aching. Smile even though it's breaking. When there are clouds in the
Quadratic and cubic functions have inverses. The graphs below show the inverses of the quadratic parent function and cubic parent function. The parent functions are shown in blue, and the inverses of these functions are shown in red. Notice that they have been reflected across that line y equals x, the dashed diagonal line going across the screen, just like we've talked about in the previous video. So notice that the inverse of f of x equals x squared is not a function because it fails the vertical line test. However, if we limit the domain of f of x equals x squared to x is greater than or equal to 0, its inverse is the inverse function square root of x. So we take the parent function, not the inverse, but if you take the parent function and only take the x values greater than or equal to 0, then reflect it, then you'll end up with the parent function square root of x. But in our picture, we're showing both the positive and negative, so really what we're just looking at is the top half of that red graph to be the inverse function. A radical function is a function whose rule is a radical expression. Makes sense, right? A square root function is a radical function involving the square root of x. The square root parent function is f of x equals square root of x, which we've seen before, and we also have the cube root parent function, which is the cube root of x. So let's graph each function and identify its domain and range. So here we have f of x equals the square root of x minus 3. So for this example, we can make a table of values, but we need to make sure we plot enough ordered pairs so that way we can see the shape of the whole graph. Because the square root of a negative number is imaginary and we cannot graph imaginary numbers on the xy plane, we will choose only non-negative values for x minus 3. Just a friendly reminder, here's the square root parent function y equals the square root of x, and we've talked about this I think it was the first 6 weeks, so it's been a little while. But we have this graph, and these are our parent points. So we're looking for a graph that looks something like this, even though it may be moved around a little bit. So here you can see I've chosen the values 3, 4, 7, and 12. These numbers, there's really not anything too special about them except that we wanted to make sure that the radicand, the number underneath the square root sign, is no smaller than 0. So it can be 0 because the square root of 0 is 0, as seen when our x value is 3, but we don't want any numbers smaller than that, otherwise we would have imaginary numbers. So I picked 3 as the smallest number and went up from there and just picked a few more points. So I got 3, 0, 4, 1, 7, 2, and 12, 3, and if we graph those, you can see the shape of the square root function right there on the right hand side of your screen. The domain for this graph is a set of all x values where x is greater than or equal to 3, and the range is y is greater than or equal to 0. Let's do the same thing with a cube root function. So here we have 2 times the cube root of x minus 2. So again, let's use a table of values, and we want to make sure that we get enough ordered pairs to see the shape of the curve. We'll want to choose negative and positive values for x on this case, because remember the cube root parent function, the cube root of x, it has that S-shaped curve, so our parent points, we chose some negative, we chose 0, and we chose some positive. So we need to make sure that we get some negative numbers and some positive numbers to see the entire S shape of the cube root the cube root function. So here we've chosen negative 6, 1, 2, 3, and 10. And you can choose whichever points you like, just enough so that you can see the shape of the entire graph, which you can see here on the right-hand side of the screen. The domain is the set of all real numbers, and the range is also the set of all real numbers. The graphs of radical functions can be transformed by using methods similar to those we've used before with linear, quadratic, polynomial, and exponential functions. But for this lesson, we're just looking at the square root functions and the transformations of these. Okay, don't let this table overwhelm you. You have seen most of this before. So if we have the function f of x, which all of our examples will be looking at the square root of x or cube root of x, but if we have a function and there's something added at the end, for example, in this first row right here, we have the square root of x plus 3. That plus 3 is outside of the radical sign, so it means that the y values have been added, 3 has been added to the y values, so that means we've gone up 3 units. Or if there's a minus 4, that means we've gone down 4. If we are adding or subtracting something inside with the x values, because it's set up as x minus h, anything that's written down next to the x value, really it's the opposite of what it looks like, just like it always has been for previous examples we've looked at. So here we have x minus 2. That minus 2 is inside the radical with the x value, so that means we're doing the opposite of what it looks like. So we're taking that minus 2, that means we're actually going 2 units to the right. A plus 1 means we're going 1 unit to the left. If we have a number all the way in the front of our function, away from the x, then that means we're multiplying the y values by that value, the a value. So here we have 6 times the square root of x. That means that the y values are being multiplied by 6. In other words, there's a vertical stretch by a factor of 6. Whereas if there's a 1/2, the y values are being compressed. They're being halved here. So they're getting smaller. So this would represent a vertical compression by a factor of 1/2. If we have x being multiplied by something inside the radical, remember it's the opposite of what it looks like. So here we have 1/5 times x. That actually means we're taking the x values and stretching them or multiplying them by 5, even though it looks like it's dividing. Whereas if we have 3x, we're actually dividing by 3 or multiplying by 1/3, a horizontal compression by 1/3. And then we can also have reflections. Depending on where the negative sign is, will tell us if we're reflecting across the x or the y axis. So if we have a negative sign in the front, that means the y values are being multiplied by -1, so it's getting flipped upside down, or you can call that a reflection across the x-axis. If it's inside with the x values are being multiplied by a -1, so they're flipped across the y-axis, so that's a reflection across the y-axis. So using the graph of the square root of x as a guide, describe the transformation and graph the function. So here we have g of x equals the square root of x plus 5. So this plus 5 is outside away from the x, so that means it's for the y values. So since we are adding 5 to the y values, that means we've moved our graph up 5 units. So in the blue graph, you can see that's our parent function, and the red is our new function. Let's look at another one. So here we have g of x equals 1/2 times the square root of x. Again, that's not with the x values, so we're multiplying the y values by 1/2. So this is going to be a vertical compression by a factor of 1/2. So it doesn't move left or right, just the y values are being multiplied by 1/2. So we can summarize the transformations of square root functions as seen here. So the value for a will tell us if it's stretching or compressing based upon if it's a number greater than 1 or less than 1. And if it's a negative number, that means we're reflecting it across the x-axis, and if it's positive, then we'll just leave it the same. If our h value, if we have an x minus h, that means we're moving it to the right, and then x plus h means moving it to the left. Plus k would be moving it up, minus k would be moving it down. And then if we have, for whatever's being multiplied in front of the x, so if it is a number, this is where it's kind of confusing for this because it's set up as 1 over b, which makes it look like the opposite. Just like this, it's set up as x minus 8, so it makes the sign look the opposite. But just go with what you remember. You know, if it has a number greater than 1, then it's being compressed, and less than 1 would be stretched when it comes to the x values. and if it's negative, you're reflecting it across the y-axis. So using our parent function as a guide, let's describe the transformation and graph this function. So we have g of x equals the negative times the square root of x minus 4. So that negative sign means we're going to reflect it across the x-axis. And then the minus 4 means we're going to move it 4 units to the right. So if the blue graph is our parent function, the red one seen there has been reflected across the x-axis and moved 4 units to the right. Here's another one, the square root of negative x, then plus 3. So the negative sign in front of the x tells us we're reflecting it across the y-axis, and the plus 3 tells us we've moved it 3 units up. So again, in blue we have our parent function, but in red we have our transformed function where it's been reflected and translated up. Okay, let's kind of do this backwards now. We're given a description and we want to write the new function for g. So if we have the parent function, the square root of x, and it's reflected across the x-axis, compressed vertically by a factor of 1/5, and translated down 5 units, let's figure out what each of those things mean whenever it comes to our function. So a reflection across the x-axis means that a will be negative. The number in front of the function will be negative. A vertical compression by a factor of 1/2, the y value is being multiplied by 1/2. So between the reflection and the compression, that tells us that a will altogether be a negative 1/5. So in the front of our function, we'll have a negative 1/5. And then translation 5 units down means that k will be a negative 5. So the a and the k are the only things that have changed for our function. So whenever we write down this transformation, we will have g of x equals negative 1/5 times the square root of x minus 5. In addition to graphing radical functions, you can also graph radical inequalities. So use the same procedure you've used for graphing linear and quadratic inequalities. So let's look at this one. We have y is greater than 2 times the square root of x minus 3. So if we use the equation, so if we make that inequality symbol an equal sign, we can make a table of values. So we chose the values x1, 4, and 9 for the x values, so that way the radicand would not be negative, so we wouldn't have any imaginary numbers. When we plug that in, we get negative 3, negative 1, 1, and 3. So using that table, let's graph what we can call the boundary curve, seen here as a dashed line since the inequality sign is greater than. And we will shade the area above it because we're looking for the y values that are greater than that curve. Please note that we are not shading anything that is to the left of the y-axis because the x values cannot be negative, otherwise that would give us imaginary numbers. So if you were considering that this was a parabola turned on its side, you would not want to go past that vertex. Let's look at another inequality. We have y is greater than the square root of x plus 4. So let's use the related equation y equals the square root of x plus 4 to make a table of values. So we can have x values no smaller than what will make the radicand 0. So an x value of negative 4 would make it 0, so we can choose the smallest number as negative 4 and go up from there. So we chose negative 3, 0, and 5 to get 0, 1, 2, and 3. So if I graph these, as seen in the dashed line, remember that it's dashed because it's a greater than, not a greater than or equal to. So since it's a greater than, it is dashed, and we will shade above it since it's a greater than sign. And remember, we're not going to take it past that point that would be the vertex if it were still a quadratic function. So at the very end of it there, that's where we'll stop the shaded region, but we're shading everything above it. Let's look at one that's a little different. How about a cube root function? So we have y is greater than or equal to the cube root of x minus 3. So again, let's use a table of values. So, and we'll use the equation y equals the cube root of x minus 3. Remember that it's okay to pick numbers that are negative, that would make the radicand negative for a cube root, because we can take a cube root of a negative number. So we picked some negative numbers, 0, and positive numbers, just to see the entire graph here. So this time we are using a solid line on the graph because it was a greater than or equal to sign. I just realized there was a little typo there, so I fixed it. The inequality sign is greater than or equal to, so we will use that should say a solid curve. Sorry about that. And we'll shade the area above it. Okay, well that's it. I hope that was clear, and if you have any questions, let me know. I will see you in class. Bye.